Bem-vindos ao dia 2. Dia 2, Leandro.
Dia 2.
Good Morning Simulation. Bom, tô aqui com o meu parceiro, que é o cara que vai saber todos os spoilers, que sabe muito melhor do que eu o que vai acontecer nesse dia 2. Então, Leandro, por favor, fala para o pessoal aí o que vai acontecer hoje no dia 2.
Joia! Hoje no dia 2, pessoal, a Mai Doan, ela tem uma grande experiência na área de óleo e gás e também uma grande experiência em análises complexas, com a utilização do Abaqus CAE. Ou seja, ela vai mostrar aplicações de não linearidade como contato não linear, grandes deslocamentos, aplicação em materiais não lineares como compósitos, borrachas. E aí ela vai mostrar como o Abaqus é poderoso exatamente para captar esse tipo de efeito onde envolva grande complexidade.
Legal. Então, pessoal, aproveitem a sessão. Bom dia para vocês.
Good morning, everyone. My name is Mai Doan. I'm a worldwide simulation consultant based in Austin, Texas. And today I'm going to present from SolidWorks to next level simulation with Abaqus. So let me ask you a simple question. Have you ever had a simulation that just wouldn't converge, no matter what you do? Most companies who use SolidWorks start with SolidWorks simulation, and it works well until the physics becomes too complex. And that's exactly what we're going to talk about today. So for the agenda, we'll cover 6 things. Why nonlinear studies fail, when to move to Abaqus, how Abaqus solves it, real-world examples, cloud computing, and key takeaways. So let's get started with why nonlinear studies fail. Most nonlinear studies don't fail because the engineer did anything wrong. They fail because the physics is too complex. You've probably seen this in SolidWorks simulation. This is an error message when nonlinear studies are not converging. So there are 3 main sources of nonlinearities: geometry, contact, and material. The real challenge is when all 3 nonlinearities happen at the same time, especially when changes are abrupt. For example, when contacts open or close. That's when convergence becomes very difficult. So when to move to Abaqus? Most companies start with SolidWorks simulation. As their simulations become more complex, more nonlinear, they eventually need Abaqus. So when to move from SolidWorks simulation to Abaqus? SolidWorks simulation is best for linear analysis, small deformation, early design validation, and fast iterations. Abaqus is needed when you have complex contact, large deformation, advanced large deformation or extreme deformation, advanced materials like hyperelastic, composite. You need it if you need to model damage and failure, and also you need it for applications like drop test, impact, so extreme nonlinearities. So Abaqus is not a replacement, it's a natural next step as complexity increases. Geometry and contact nonlinearity when the structure changes. So let's talk about geometry and contact nonlinearities. Here, when the dome touches the bottom surface, its shape is changing as it deforms. That's geometry nonlinearity. Now, when the dome makes contact with the bottom surface, that's contact nonlinearity. And it is not smooth. It's abrupt. It's on or off. This sudden or abrupt change is what makes contact difficult to converge. In SolidWorks simulation, we define contact using contact pairs. This works well when contact is predictable, like this dome example on the left. Now, when you have an example like the one on the right, a ball splitting hairs. In this case, any hair can touch the ball. Any hair can touch another hair. Contacts open, close, and change constantly. In this case, defining contact manually is almost impossible. That's when we use general contact in Abaqus. The third source of nonlinearity is material nonlinearity. For metals, once you pass the yield strength, the material behavior becomes nonlinear. For materials like rubber, gasket, knit-knoll, the response is nonlinear from the beginning. And composites are even more complex. They are direction dependent, meaning they don't behave the same in every direction. They are layered and they fail progressively. Composites are not just nonlinear, they are nonlinear layered structures. And how you model them determine the accuracy of your results. Composite damage and failure. Unlike other materials, failure in composite is not one event. It's multiple mechanisms happening together. Abaqus can simulate interlaminar or delamination, where layers separate from each other. This is critical because once layers lose adhesion, the structure quickly loses stiffness and load carrying capacity. Abaqus can simulate intralaminar damage, things like matrix cracking or fiber failure. To simulate composite failure accurately, Abaqus offers multiple advanced techniques. Cohesive elements and VCCT, which stands for virtual crack closure technique, capture delamination. XFEM handles crack propagation, and continuum damage models represent progressive material degradation. The power comes from combining these approaches to reflect how damage actually develops in real composite structures. So let's talk now about packaging. When you move to Abaqus, you unlock the full ecosystem. Abaqus, proven finite element analysis technology, arguably the best nonlinear solver or the nonlinear technology on the market, both for its implicit and explicit solver. EyeSight enables you to automate workflows, perform parametric and optimization studies using DOE, design of experiment, Monte Carlo, and more. Tosca is used for structure and fluid flow optimization for conceptual and detailed analysis. FESafe is the market leader for fatigue and durability to predict and analyze product life. With FESafe, you can perform stress and strain-based fatigue, so run high cycle fatigue and low cycle fatigue. FESafe comes with a predefined material database. So next, how Abaqus solves it. Let's focus on how Abaqus solves nonlinear studies. Abaqus comes with two parts. You can do all the pre-processing and post-processing in Abaqus CAE, complete Abaqus environment. And underneath, you have two complementary solvers, Abaqus Standard and Abaqus Explicit. Abaqus standard is used for nonlinear static problems and slow dynamics. It is perfect for nonlinear behavior like nonlinear contact, nonlinear materials, and large deformation. You can use Abaqus standard for a wide range of multi-physics procedure, such as couple temperature and displacement, but also couple thermal and electrical, acoustics, electromagnetics, electrochemical, and more. Abaqus explicit is used for high-speed transient dynamic events, so fast and short events. Abaqus explicit is also suited for highly nonlinear quasi-static events. We'll talk more about this topic in a minute. You can see here typical explicit applications such as crash test, forming, deep drawing, metal rolling, blast, and a lot more. So implicit versus explicit. We all know that implicit and explicit are different solvers, but what most engineers don't know is how they work when it comes to convergence. Implicit tries to find equilibrium. It requires convergence. Explicit does not try to converge. It comes forward in small time steps. So this is really important difference between implicit and explicit. And that makes explicit very robust. And this is why explicit can solve problems that fail in implicit. And even static problems can be solved with explicit using quasi-static techniques. So that technique is that we apply the load slowly, we keep inertia small, and we solve them without equilibrium iterations. And that is why explicit can solve problems that you cannot obtain result, you cannot obtain convergence, and that fail in implicit. And here we have this sheet metal forming problems that was solved using explicit in a quasi-static way. So real-world examples. Here we have a real case, a simulation study with a friction coefficient of 0.4. In this case, SolidWorks simulation struggles and Abaqus solves it. So this looks like a simple rotary selector, but it combines three things that are extremely nonlinear: a hyperelastic core, an interference fit, and a friction coefficient of 0.4, all interacting at the same time. In SolidWorks simulation, you'll see a warning when friction exceeds 0.2. And even with a frictionless contact, meaning a friction coefficient of 0, this analysis didn't solve in SolidWorks simulation. In Abaqus, on the contrary, the same model solves successfully with the realistic 0.4 friction coefficient. So same model, same physics, different outcome. No convergence in SolidWorks simulation, full convergence with realistic friction of 0.4 in Abaqus. And that's the power of a more robust nonlinear solver. Here we have an example of a multi-strand wire using general contact. So it is difficult in this case to predict how contacting surfaces changes during the simulation. As the simulation progresses, surface will contact with different surfaces, and the change is continuous throughout the whole application. So the solution here is to use general contact in Abaqus, which is powerful and yet easy to use. Progressive damage and failure. Here we have an example of the crushing of a column. So when you need damage and failure, use Abaqus. Damage and failure are not available in SolidWorks simulation. On the left, we model damage initiation only. This means we only predict when damage starts. On the right, we model both damage initiation and damage evolution. This means we allow damage to evolve following that failure process. Here we have an example of a pin join model. So when contact needs help, contact stabilization is a good option. In this pin join model, the vertical pin is held only by two clevises with the gaps between the pins and the clevises. So what happens when we have these gaps is the model will experience rigid body motion. So to avoid rigid body motion, we use contact stabilization, which adds damping to help the model settle in order to get convergence. So think about damping as a numerical jelly to hold that whole assembly together. And as contact established, the numerical jelly melts away. When structures interact with flowing material, we need to use CEL, or couple Eulerian Lagrangian. So here we have the simulation of a fluid-filled tank impact and a tank sloshing. When we have structures interacting with flowing material, we need to use CEL. So the structure is still modeled the way we used to, which is using Lagrangian elements, but the flowing material is handled differently using Eulerian elements, so it can move freely without destroying the mesh. This lets us capture fluid-structure interaction, even under extreme motion. Here, the tank deforms on impact, while the fluid sloshes and loads the structure dynamically. Here we have a tank sloshing. The fluid motion, not just the structure, drives the load. When physics include fragmentation, we need to use SPH, or smooth particle hydrodynamics. So when we have material, when material breaks apart, physics include fragmentation. That's when smooth particle hydrodynamic comes in. So SPH is designed for problems where material breaks apart, flows, or separate completely. SPH replaces the mesh with particles. Those particles can separate, collide, and flow. On the left, SPH is used to represent solid material with a projectile impact analysis. You can see that the material fractures and separates. On the right, we have dip painting analysis, which is used to find regions of the vehicle chassis that fail to converge. So when deformation becomes fragmentation, SPH is the right method. Obviously, CEL and SPH are not available in SolidWorks simulation. That's when we need to move to Abaqus. DEM, discrete element method. When we have materials that flow, such as powders or particles, we need to use discrete element method as shown in the examples here. So these are physics that are simply not available in SolidWorks simulation. Cloud computing. this is a very powerful capability of Abaqus, and it is not, again, available with SolidWorks simulation. So this is a major advantage in Abaqus. There are 3 common challenges. The first one is not enough hardware. The second one is simulation is running too slow. And the third one is engineers have too many cases to run, and cloud computing solve all these 3 challenges. Here is an example of a bold pretension analysis of an engine block. We have an implicit static analysis with 17 million degrees of freedom, or almost 6 million nodes. Using cloud computing, using local computing, this study took about 48 hours. Whereas using cloud computing, you can speed it up by 8 times by using 36 cores, or 20 times using 144 cores. With cloud computing, you can run much larger models much faster. So more core, shorter simulation time. Here, we have an explicit example of a drop test with 340,000 degrees of freedom. Here, you can see that the speed up can be 4 times using 8 cores, or 8 times using 18 cores. With cloud computing, even complex simulation like drop tests run in minutes instead of hours, so engineers can iterate much faster. So instead of waiting, engineers can iterate and make decisions faster. Finally, last section is the key takeaways. So the question is, when do you need to move to Abaqus? You want to stay in SolidWorks simulation if you have linear behavior, small deformation, simple contact, everything converges. You want to do fast design iteration. You want to move to Abaqus when your simulation fails or it doesn't converge. You have large or extreme deformation. You have complex or unpredictable contact. You want to model advanced material like rubber or composites. You need to model failure and damage. You need to model drop test impact, crushing. So SolidWorks simulation helps you design. Abaqus helps you predict real-world applications. This is not a replacement, it's an expansion. And the question is not if you need Abaqus, it's when you need Abaqus. So with that, this concludes my presentation. Thank you for your attention.
Finalizamos mais um dia, dia 2, encerrado. Bom, Leandro, faz um resumo novamente, acho que a tua função aqui, a gente precisa de você para algumas coisas aqui.
Joia.
2 delas é resumo e spoiler, resumo e spoiler, resumo e spoiler.
Vamos lá.
Bom, faz um resumo do que aconteceu nesse dia de hoje e dá um pequeno spoiler, porque amanhã cedo a gente explica um pouco melhor o que vai acontecer no dia 3, mas conta um pouquinho o que aconteceu hoje e fala um pouquinho sobre amanhã, por favor.
Combinado. A Mai Doan, ela tem uma grande experiência nessa área de óleo e gás e principalmente trabalhando com Abaqus, né? Ela mostrou principalmente os 3 tipos de não linearidade que o Abaqus ele roda muito bem, né? Ele consegue ter uma precisão muito grande nos resultados, porque ele foi desenvolvido para isso, ou seja, contato não linear, grandes deslocamentos, materiais não lineares. Ela abordou sobre a questão de borracha, a questão de compósitos laminados, né? E agora no dia 3, o Ramesh ele vai falar sobre a plataforma 3D Experience, também abordando, né, os tipos de simulação, né, os 4 tipos de simulação que nós temos, ou seja, simulação plástica, eletromagnética, fluidos e estrutural, porém isso tudo rodando na nuvem e contando com toda a tecnologia colaborativa com a plataforma 3D Experience.
Bom, muito bem. Então, vamos segura aí. Amanhã cedo a gente começa o dia 3, que é o último dia do Good Morning Simulation, e a gente espera todos vocês aqui conosco, tá bom? Valeu!